Okay, today, like I said in my announcements, is going to be a slightly different class. The first half, roughly speaking, we're going to be just discussing some algorithms that we can use to simulate evolution. And then in the second part, there's no lecture essentially. It's just practice time for you guys to practice simulating what you've learned in the first part. And we can either do that in here, we can take a vote, or we can go outside and sit in the shade. Or you can sit in the sun if you really want, but I'll be in the shade. Really, that's a chance for you to have a go at coding. Like, I'll give one example, but you can code up any of the examples that we've been through so far. Yeah, there's a coding aspect to the project, so that should help you with that as well. Yeah, really, that's an opportunity for you to try and implement these ideas and then ask questions of me whilst I'm there. Okay, so any questions before we get started? No? Good. Okay, so what did we do in the last lecture? Last lecture, we were continuing this interest-specific model of competition. So you can think of this as resource competition typically. And we saw that under certain circumstances, this could lead to this process of evolutionary branching, right? So this is generating diversity. So we start off with just one phenotype in the population, and then over time, after we approach a singular strategy, we converge to that singular strategy, and then it is evolutionarily unstable, which means that it's actually a fitness minimum once you reach it. That means that mutants either side can invade, and they can coexist in this case. They then diverge, and then eventually in this model, they reach other branching points as well. So one of the issues sometimes with doing this kind of adaptive dynamics analysis is that you can it's relatively straightforward to understand that first stage when there's just one type in the population, okay? And then when you go up to having two or more types in the population, things inevitably get harder. Now we have to think about, say, if you've got two resident types, you need to think about your selection gradient at each of those resident types. And what happens if a mutant appears next to this resident or next to this resident, okay? So that makes it harder. I mean, some of these models are tractable, but sometimes it's not, especially when it goes into higher order numbers of branching, in which case you might want to simulate things. Other reasons you might want to simulate things are potentially to relax some of the assumptions of your analysis, and we'll talk about that in a moment. Okay, so we're going to be talking about evolutionary simulations in general today. We're going to be talking about something called the Gillespie algorithm, which some of you may or may not have met before. And then the one we're really going to focus on is this adaptive dynamics simulation algorithm. Okay. So this was the example of a simulation that I showed at the end of last lecture. So what we've got here is we've got time in an evolutionary sense running on this vertical axis here. And then we've got here whatever our trait is that's evolving, so just some arbitrary phenotype X. So this could be, for example, this could be a measure relative to some reference point of like body size, say, so whether you're larger than some reference body size or smaller. It could be some spatial location that you prefer to nest in. It could be sort of relative to, say, water, what's your preferred pH? Could be any number of different things. Could be the relative size of seed that you prefer. The fact that this is at 0 is really just for mathematical convenience. One could rescale this to any number, okay? So we start off by zooming here, down with this phenotype at some relatively low value. Here happens to be close to minus 1.5, which I've just set up as the boundaries here. This number, there's no significance to this. It's just, for this particular example, okay? And then this shading here is just indicating what is the frequency. If you think of this as like each slice in time, so maybe it's Tn and this is Tn plus 1 or something, right? At each slice in time, this shading is just showing what is the frequency of the phenotypes. So you can think of these as just a load of slices that have been put together. Just get rid of those. So in this case, it crosses this blue line, which happens to be a branching point, but it's only a branching point when there are two types in the system. So to start off with, this is not a singular strategy, okay? We cross over here, we converge towards this singular strategy at 0 in the middle. So this is convergence stable. So we have C is less than 0, but it was evolutionarily unstable. We work out the second order partial derivative of our invasion fitness with respect to our rare mutant and evaluate it at the singular strategy, you end up finding that this is greater than 0, okay, in this particular example. So that means essentially we have something that looks like this. I just sketch out at 0, our invasion fitness at 0 ends up looking something like this. Okay, so this is my point 0 here. It means that mutants that are a little bit either side both have higher fitness. They can both invade. Okay, so that's what happens here. We have this branching process where mutants on this side of this red line and mutants on this side of that red line are fitter and they can coexist with each other. This is this process of disruptive selection. They're being pushed apart. They're diverging from each other. Eventually, in this particular model, they each reach a second branching point. These are referred to as co-singular strategies. So there's more than one of them. And then again, we go through a similar process of branching either side here. In principle, in different models, things may branch once, they may branch many times, they may branch an infinite number of times. Okay? It just depends on the model setup. We can see here, like by doing a simulation, we don't, we get out the key findings that we do from the adaptive dynamics analysis. We can check here, this red line, for example, is plotted from what we would derive analytically. And also these blue lines are as well. But we can kind of see a bit more about the process that's going on here. This evolutionary time, by the way, we'll talk a bit more about the algorithm that was used to generate this later on. This really can be thought of as number of mutations. So because this is a simulation kind of representing adaptive dynamics, the simulations don't actually have a full separation of ecological and evolutionary timescales. They kind of do a sort of a semi-separation. It's still essentially assuming there's a low mutation rate. But you can actually vary that mutation rate by varying different parameters in the system. And you can think of each of these time points essentially as a mutation event. That's kind of what's going. So it's a number of mutations on this y-axis. Any questions about simulation? Okay, so this is what kind of thing we want to be working towards. So I just said this, in the reasons why we might want to do evolutionary simulations, they can complement any sort of other analysis we might do, whether that's algebraic or whether it's numerical. Often in my research, there's a certain amount that you can do algebraically. For example, one can often derive things like selection gradients. You can write down your invasion fitness using the next generation method. That's usually fairly straightforward to do. You can do things like derive the selection gradient from that invasion fitness. You can maybe find out what your condition for evolutionary stability is. However, often that might be the limit of what you can do, and you might just have some horrible long expression, in which case you have to then solve it numerically. Okay, so there's sometimes a bit of a blended approach between these things. But our simulations can add another way of trying to understand what's going on, and they can relax some of those assumptions. They might also allow us to include some other forms of complexity that are often harder to include in these types of models. So examples here, stochasticity. I mean, everything that we're doing here has been deterministic, right? We say that there's a rare mutation. Mutations are random events, but we're kind of glossing over that kind of fact here, right? We assume that a mutation eventually occurs, okay? You could have greater stochasticity, for example, environmental factors, environmental noise. We're treating our populations as being infinite, essentially, which we're really, we often talk about these as being population sizes, but really they're population densities. Okay, so essentially we're talking about infinite populations here. And we might want to have individual level behavior as well. So, often in these models, we can capture a greater amount of heterogeneity if you're simulating things. In the adaptive dynamic simulations, not so much, but in the Gillespie algorithm we'll talk about, that's generally a better way of incorporating these individual level effects that you might care about. And also something like spatial structure as well. If there's, for example, in an infectious disease, people within the same household or town may be more likely to infect each other than people that are in different locations. So you might want to take into account some of these effects. So simulations can often be a better way of attacking some of these approaches, where you might be able to make limited progress analytically. So there are many different ways in which we can simulate evolution, and we're just going to cover two today, so this is not exhaustive. But two common methods. One is the Gillespie algorithm. This is named after a physicist, Dan Gillespie, who popularized this, although he didn't invent it himself, in the 1970s. And this first algorithm is essentially a way of, it comes from sort of chemical reactions, okay? And the idea is sort of, given a number of particles that are moving around, or a number of molecules, you know, what's the expected time till the next event, you know, the next chemical reaction that we expect. We can apply the same ideas to, say, a biological population rather than a chemical reaction. We're maybe thinking about some biological process. So what's the time till the next birth or the next death or the next infection and so on. So here we essentially sum up all the possible rates that we have in our model. So by that, I mean, you know, we have a total birth rate, we have a total death rate, and so on. So we add up all of those different rates. And then because in our sort of standard ODE models, essentially all of these processes are exponentially distributed, we can then calculate an expected time using an exponential distribution. So an expected time to the next event. I'll go through this a bit more in a moment. One of the things this assumes is that a probability that an event occurs is, or occurring in the next instant of time, it doesn't depend at all on what's happened previously. Okay, it depends on the current state of the system, but there's no memory from when the last event occurred. Okay, so this is a Poisson process, right? So we can then write down a function that gives us this property of being memorylessness. Okay, so what does that function look like? Well, because these are exponentially distributed, if we have a rate or a total rate of all events, in this case, maybe being lambda, we can write down what's called the probability density function of our time tau. And this time tau is the time until the next event occurs. Okay, so this is just some function of tau. And this works out to be from the probability density function of an exponential distribution with mean lambda. This is lambda e to the minus lambda tau. Okay, this all just basically comes from the fact that it's exponentially distributed. Essentially, like I say, you don't know the time until the next event occurs, but you assume that and this is what we want to work out, but we're assuming that just because an event has occurred at, say, t equals 5, that doesn't mean that it's more likely, say, that an event is going to occur at t equals 6 or t equals 10 or whatever. This rate lambda basically treats everything kind of as resetting, if you like. That there's no memory in the system. Yeah.
You said this is a Poisson process, but we're not using Poisson function.
You can relate the exponential to Poisson process, basically. Yeah, that's kind of, I don't want to go too much into the theory of this. I want to focus more on the application of the algorithms, but you can relate the exponential to the Poisson. Okay. So that's our probability density function. If we want to determine that time tau, which is the thing we want to use in our simulation algorithm, you know, we want to know when is the next event happening and then find out what event does happen. So the time till this next reaction here in this classical sort of idea of a Gillespie chemical reaction. When I say reaction in a biological sense, you can think of just some biological process. Time till this next event tau uses the inverse of our cumulative distribution function. So the CDF of some probability distribution. Again, we're using this exponential distribution. All we're doing is rearranging this for tau. And or we rearrange our cumulative distribution function. So we arrange this for tau. We have minus log of a random number. And this random number is assumed to be uniformly distributed between 0 and 1. And then we divide by the total rate lambda. Note that because this R1 is between 0 and 1, log of that number is going to be negative, which is why there's a minus sign at the front. So those minus signs cancel. This will be greater than or equal to 0. Well, technically, actually, this will always be greater than 0. There's a step that you should do, which I'll talk about in the algorithm briefly. You have to check that this lambda is positive, obviously. So this is for lambda greater than 0. Remember, this lambda is basically telling you what are the rates that your events occur at. Your rates have to be non-negative, right? If no events occur, or if there's no rates occurring, all of your rates are 0. That means that there can never be, say, a birth, there can never be a death, and so everything's trivial. Therefore, you can't calculate a time. Okay, so in practice, what we're doing is we generate this random number that's uniformly distributed between 0 and 1. We plug it into this formula. This gives us this tau, and this is the time until a next event occurs in our simulation. We then find a second random number, or generate a second random number R2, that's again uniformly distributed between 0 and 1. And then to choose which event happens, we now look at all of the rates, all of the individual rates that come together to form this total rate lambda. Look at all of those individual rates, say for your births, for your deaths, and so on. And then we use a weighted probability distribution to choose which event is going to occur. In other words, the events that have make up a large proportion of this lambda should be more likely to happen. So if your births were occurring at a much higher rate than your deaths, then you'd be much more likely to expect a birth than a death. Okay, so this gives you your time at which the next event occurs, and then after that we work out which event is the thing that's actually happening. So if you want to do the Gillespie algorithm, this is the sort of the pseudocode for it. The first thing we need to do is we need to set up some initial time t. So just for arbitrary sake, we'll set t to 0. And we have an initial state, which I'll call state. This is just some state vector. When I'm saying a state vector, or even typically it'll be a state vector, it's really just a record of what's going on in your population. So for example, in the kinds of models that we met before, like the intraspecific competition model, this would be, say, the number of individuals in phenotype I would just be your state vector. Okay, so we set it to some initial state. It could be that state vector could be, say, whether an individual, if you've got a population of, say, size n, it could be individuals. If you're tracking those individuals, it could be whether they're alive, dead, or they have some particular status as well. Okay, so whatever your state vector happens to be, whether it's at like a population class level or whether it's at an individual level, we have to set it to some initial state to start with. Then we carry out our main simulation loop. So the first thing we do is we calculate our total rate. So this is our lambda from our previous slides, essentially. So you just sum up all the possible rates in the system. We then check, is lambda equal to 0? If this total rate is equal to 0. If it is, then that means that nothing's happening. So we just have to terminate our simulation. It's important to do this step just in case there's a bug in your system. Otherwise, things can kind of go negative and crazy. We then advance time, and we generate these two random numbers, R1 and R2. So we calculate this time like I've just described. Tau is the time that our next event occurs. We do minus log of this first random number. These random numbers, remember, they're uniformly distributed between 0 and 1, and we divide by the total rate lambda. You can see here, if lambda is very high, then this tau is going to go low. So the time to the next event should decrease on average as you increase the rates in the system. So the faster things are happening, the more likely it is that an event is going to occur in the shorter time frame. We then use this second random number. We multiply the second net random number, R2 here, by the total rate, which in our case is lambda. And that's going to give you some real number between 0 and lambda. Yes?
Is there any specific criteria to picking the two random numbers?
Just that they need to be uniformly distributed between 0 and 1.
Oh, okay.
Okay, so yeah, you don't want to choose say a normal distribution or something like that, because then it will be biased towards 0.5. But it needs to be between 0 and 1. The reason it has to be between 0 and 1 is for this step, for example, is because you need to select you're essentially doing a weighted probability distribution, and you need to select an event that goes, if you sum up all of your rates, that gives you your total rate. You don't want to have a number greater than 1, your random number, because otherwise you'll be selecting an event that's above your total rates. Sometimes it's a little bit harder to explain than actually to implement. So I might put this on a homework assignment, we'll see. But I'll probably give you some hints to get there. Okay, we update next our state vector. So the thing we defined at the start, the state vector is just our population that we've got. And we update it based according to this chosen event. Okay, so how we do that really is we have, say, a vector that defines the rates for, say, our births, our deaths, or what is happening at an individual level. We take a cumulative sum over that rate vector. And then we look at this number, R2 times total rate, and we see when is this number less than the first entry in our, when is the first entry in that cumulative sum vector that is greater than this? Okay. Essentially, you can think of this as, one way to think of this is say, okay, suppose this is my total rate, just some line here of length lambda. And then this is divided up into different chunks of different lengths. So for argument's sake, let's do, this is maybe my births. Perhaps this is deaths. Maybe this is infections. And maybe this little window down here is maybe migration. Something, whatever happens to be, right? And then because we're taking this number here, R2 times total rate, or lambda in this case, that R2 times lambda is going to fall into one of these windows, right? The bigger these intervals are, these windows, the more likely it is, say here in this infection window here, it's kind of saying the most likely event to occur is going to be an infection, because infections have the overall biggest rate. So when we do this step of taking this uniformly randomly distributed number times by our total rate lambda, what we're really doing is we're placing this number R2 lambda somewhere along this line and seeing which window it falls in. So by taking a cumulative sum, that's just an efficient way of finding which window it falls into. Okay. And then all we do is we keep repeating this. We repeat it until our t is greater than some max time. And then record your output and return, do whatever you want to do with it. Okay. So this is a very common method that's used not just to model evolution, modeled, used in chemistry and physics. It's used in other areas in biology. So, for example, understanding how enzymes might interact with proteins. It's used to understand population dynamics. It's used to understand evolutionary dynamics. One of the reasons it is used is because it is relatively straightforward to implement. The only things that we need to generate are these two random numbers, sum over all of our rates, and then find which event is most likely to occur. So it's a pretty simple algorithm that is very adaptable to different scenarios. Okay. Yes.
Quick question.
Yes.
Couldn't we also use R1 lambda because R1 and R2 are distributed?
Very good question. The reason that we select two numbers is because you don't want there to be any correlation between the time that's occurring and which event that you're landing in. So there is actually a way that you can do this. You can rescale and reuse R1 if you want to, but you have to rescale it in a special way. which I'm not going to go into, but there is a way to reuse it, which is slightly more efficient, which matters in really big simulations. But basically, these two things need to be independent so that the event that you're choosing, also the time to the event that you're choosing, doesn't correlate at all with which event it actually is. Okay. Yeah, you don't want it to basically bias anything. That's kind of the key. But a very good question. Okay, so it's relatively straightforward to implement. And it, like I say, is flexible to many different scenarios. Once you learn this process, you can apply it to basically any system. One of the nice things about it is that it is event driven. By that, I mean that the time to the next event is based on the total rates. So if we compare this, for example, to I guess this is say like an asynchronous updating versus synchronous updating. If your rates are relatively low, that means the time can advance in these larger jumps, okay? Whereas if you sort of arbitrarily set up and say, okay, I want my simulation to update every hour or every day, you're always locked into that, right? So this can adapt to times where maybe, especially those rates will be varying over the course of a simulation. There might be times where you need very small time steps. And then there might be other periods where you can actually get away with big time steps where the rates plummet. So that adaptive time step means that it can be efficient in giving you the accuracy where you need it, where rates are fast. And you have small time steps, and then the speed advancement of jumping forward in time by bigger jumps. Whereas if you just say, okay, I'm going to have a fixed delta t, that means that you're not able to adjust to the rates varying. Okay, so it can be more efficient because it's event driven. It's very efficient, pretty efficient for small populations. Small is, you know, there's no argument here as to exactly what small means. It's going to depend on the circumstance. And it can be more efficient than other approaches, say like the adaptive dynamics one that we'll talk about in a little bit. When you have lots of individual level variation. So if you have lots of individual level variation, you might need to have lots and lots and lots of ODEs to capture that variation. Okay. But if you've got relatively small populations, it might be more efficient to actually just capture those individual level data within those individual levels. Okay. And also one of the cool things about this is in the limit of large populations, so as our population size tends to infinity, this actually approaches the underlying ODEs. So it's very easy to go straight from a system of ODEs that you have to the Gillespie algorithm. And you can then see what are the effects of the stochasticity on your model that you can write down in some ODEs. If your population sizes get very large, they actually converge. So that's kind of a nice property. One of the big drawbacks, though, is it is computationally intensive. So it's good for small populations, but as your population size or your rates grow, usually those two things will go together. The number of events that occur in the next time unit is, or rather your time to your next event is going to get very, very small. That's where updating synchronously and making these jumps can be more efficient. There is another method that I'm not going to go into today called the tau leap method, which uses this Poisson sort of process and calculates the number of events that occur in a fixed time step. That's a method that people tend to use if these populations get large. So they switch away from the Gillespie algorithm onto this tau leap method as an alternative. Okay. I wanted to introduce that because I don't want you to think that this is the only method for simulating evolution, adaptive dynamic simulation, but this is the one that I'm generally going to advise you to take this approach. You don't necessarily have to take this approach when you're simulating things, okay? But this is generally going to be faster and will be easier to plot those kinds of simulations that I showed at the start. One of the other nice things about doing this is it should hopefully allow you to check that your algebraic or numerical analysis that you've done, where you derive your selection gradients and all of that kind of that process, gives you the same answer as your simulations. Those two things should match up. If they don't match up, it suggests that one or both of those things is wrong. So they should get to the same answer by a different method. So it's a really good way of checking your own work, essentially. And it also relaxes two key assumptions of our adaptive dynamics approach. One of them is this separation of timescales. So remember, we're assuming that our population reaches some dynamic attractor, in our case, an equilibrium, separation of timescales. It's one of these assumptions. And that occurs before a new mutation arises. Now, when we're simulating these things, we can't actually let time go to infinity. We could let it approach that equilibrium, or we could actually just introduce mutations at a higher rate. If we introduce mutations at a higher rate, we're essentially just testing whether our assumption of separation of timescales changes our result. So it's a good way of checking whether this, analytical approximation that we do for mathematical convenience has any impact on the results. If it does, that's a problem, right? And we should know about it. As with any model, if you're able to relax your assumptions and check your results, however that may be, if your results are not robust, then it tells you that's a critical assumption that you've made that is maybe not realistic. Or rather, even if it's not realistic, does it matter? So there's definitely this when we make assumptions in models, we can make assumptions that are not realistic, but don't matter. So this assumption of separation of ecological and evolutionary timescales is not realistic, but actually it turns out that usually it doesn't matter. It doesn't change the outcome to these models. So unrealistic, but doesn't matter. You might have assumptions that are unrealistic and do matter, in which case you want to know about them. The other thing that we assume typically is that our phenotypes in our model are continuous. I'm putting it in a slight brackets here because not quite technically that, but we're assuming that we have essentially very small mutations, that our mutant is very, very, very close to our resident. That allows us to take our derivatives, right? So essentially we've got these continuous phenotypes with very small mutations. Now, we're still going to assume that our mutations are local, so they're not sort of massive changes in phenotype. But what we can do is we can discretize our, say, continuous phenotype. So if I just go all the way back to the beginning up here, this is some continuous interval, right? If we have in our interest-specific competition model, we let X be any real number. In reality, when I'm simulating this, I actually have to discretize it into chunks, okay? So when I do that, I'm essentially assuming that there aren't these very, very, very small mutations. There's actually a sort of a minimum mutation size. Again, that we can test to see whether that assumption in our analytic approach makes any difference. Okay. How do the simulations do this? Well, you mentioned the second one just now. We discretize our phenotype rather than assuming that it's continuous. I refer to this as a phenotype or trait space. When I say phenotype or space or trait space, all I mean is essentially what is our trait that is evolving? In this case, the model at the start, it was X. That was the trait that was evolving. And so I'm just discretizing that. This first one we relax by introducing these mutants before our resident population has approached its equilibrium. Okay. Any questions so far? In terms of the actual method then, what do we do? Well, we start in a similar way in terms of like we have to initialize a population at some particular particular phenotype. And what we're going to do is we're going to set up our ODEs for our model, and we solve them for a time window. Introduce a rare mutant, solve them for a time window. Introduce the rare mutant, solve them for a time window, and just propagate forward, okay? The only difference from our classical adaptive dynamics is we're not allowing that time interval to be an infinite amount of time. We're just going to choose some arbitrary fixed time window. Again, you might also want to check whether that time window itself has any effect on the results. Typically, it doesn't. So, like I said, we're not going to assume these large jumps in mutations. Okay, so no large jumps in phenotype space. Our mutation is going to be local. Because we've discretized this phenotype, suppose there are 100 different trait values that are possible, and you start on trait value 50. When you introduce a mutant, it can only be adjacent to the ones there. So maybe it could be at index 49 or index 51. Okay. So we're assuming local mutations, even though they're not very, 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 very small now. We solve those ODEs, like I say, for a fixed time period. We're not letting t go into infinity now. We just do it for a fixed time period. These dynamics are therefore deterministic, but then we randomly choose, which is our mutant that is going to invade. Okay, and we do this based on a weighted probability of all the types that are currently in the system. Again, one of the differences between this and the classic approach is that we're not just assuming that a mutant replaces a resident straight away. They can coexist for a while, and then if any of them fall below some threshold that we set as an extinction threshold, they just get removed from the system. So this is, let's see, we've only got a couple more slides, and then we can go on to practicing this, okay? So the first step, like I said before, is for this adaptive dynamic simulation algorithm is to initialize our populations. Okay, so we're going to start at t is equal to 0. And when I'm saying initializing the population, what I mean by this is we want to track all of our different phenotypes now in our population, whatever those phenotypes may be. And we're just going to start off with one phenotype. Okay, so we just choose one at random. And we then use our ODE solver. So for example, in MATLAB, you might use something like ODE45, or in Python, whatever you happen to use. Some ODE solver that's built in to progress time forward by t time units. In other words, you're solving it between 0 and time t, capital T here. And we're going to fix this capital T. So this isn't varying at all during our simulations. After we've done that, that just gives you some output from your ODE solver. Just, what are the current population densities of each of your phenotypes? Here, remember, we started off with just one resident phenotype. What we're really doing, the easier way to set this up is to have all of your different ODEs for all of your different phenotypes, okay? So for example, if I'm gonna allow n different phenotypes in my system, I would have a population vector that is like n1, n2, n3, and so on, up to n, little n. Maybe I start with n3 as my resident phenotype. So what I actually do then is I set all of these others to be 0. Okay, so we start off with essentially everything in the system. You're solving a big number of ODEs, but most of them are equal to 0. At this point here, we check whether anything has gone extinct. Here we start off with just one resident phenotype. We hope it hasn't gone extinct. Otherwise, it's telling us that there's no stable equilibrium. That's non-trivial. But typically, when in a more generic state, when you have many types in the system, maybe they're here as an N2 and an N4, just for argument's sake. We want to check to see whether the frequencies of these, so we want to rescale it according to the total population size, see whether the frequencies of these fall below some threshold, epsilon extinction. Okay, so we set some threshold here, maybe I set this to be 1%. So if anything falls, say, below a frequency of 1% in the population, I'm just going to set this output vector here for my ODE solver for that particular entry. Suppose N2 is equal to 0, was less than 1%. Going forward, this is now going to be 0. Okay. The next stage after we've checked for extinctions is to identify where our mutation is going to come from. Okay, so this is our sort of separation of ecological and evolutionary timescales kind of step. We need to choose where our mutant is coming from. And the reason we need to choose this is because there may be many types that are temporarily coexisting in the system. Okay, so here, for example, I've got N3 and N4 are my two types. So what do? I calculate the frequencies of all current phenotypes, which I should have done already anyway for this extinction stage. And then we determine which will be the progenitor or the origin of this mutation, which phenotype is going to be the origin, by comparing the cumulative frequencies, comparing cumulative frequencies to a uniform random number between 0 and 1. So this is essentially the same process that one uses here to calculate the time. We're choosing a random number between 0 and 1. It's uniformly randomly distributed. And we're choosing our mutant based on essentially how much of this, this window they take up. So, for example, if this line here represents 0 and 1, is the proportion of my population that is N3 and the proportion of my population that is N4, and any other types that I may have. Suppose, for example, here, the N3 makes up a bigger frequency. So this is for my N3, and this is my N4, or divided by the total population size. If I choose a random number now, it is going to place me again somewhere on this interval. The bigger this interval is, so the bigger N3 is relative to N4, the more likely it is that my mutant should appear in this window here, right? Because it's a bigger window. And that makes sense because we want our mutations to be most likely to come from the things that are most common in the system. It won't always be the case. There's always a chance it will appear in this window. But it's just more likely that it's going to come from the thing that's most common. That's how we choose which phenotype is going to be our origin of our mutation. We then have to choose what our mutant phenotype is actually going to be. We have to check that we're not on a boundary, first of all. And by that, I mean, because we've discretized our trait interval, we necessarily are going to have a lower bound and an upper bound. So we have to make sure that we don't go outside those bounds. But assuming we don't, we just choose randomly an adjacent mutant one step away from our, we choose a mutant to be one step above or below our progenitor with equal probability. So essentially, we're just flipping a coin at this point, and we say, where is our mutant going to be? So suppose, for argument's sake, I did end up with a random number in this interval here, saying that phenotype 3 is going to be my progenitor of the mutation. I'm going to then, with 50-50 probability, choose N2 or N4 to be the origin, to be the mutant that arises. Okay, so I'm going one above and one below. Like I said, you have to be careful if you're at a boundary, you just kind of reflect back inwards and it always has to be coming back in. If you're not at a boundary, you just choose one above or one below with 50-50 probability, because we're assuming that there's no biases here in the direction in which mutations occur. And then all we need to do is you introduce the mutant at a relatively low frequency. In this case, if it was N2 was my choice of my mutant, N2 is currently not in this system because it was set to 0 up here. So now I'm just going to introduce N2 at a relatively low frequency, say 1%. Doesn't really matter what you do, as long as it's a relatively low frequency. This is like my invasion fitness, right? I'm introducing a rare mutant into this system. If I had chosen N4, when I flip this coin instead, note up here, N4 is already in the system. So at this point, all you do is you just add a little bit to N4. Again, just increase its frequency by 1%. So we're having a little bit of flow of additional mutations there. But it's important not to just reset it completely, okay? So you have to be aware of that. And then finally, we just repeat this until we reach some arbitrary max time. And by this max time, this is really max number of mutations. So at the start of this, when we're setting up all of our parameters, we kind of have some evolutionary time steps. So this max time here is not, although it is a way to scale it by this big T here, we really just care about this number of mutations. So if I go all the way back to this simulation at the start, here I'd say set my number of mutations to be 2000. So once I reach 2000 loops through this process, then I can end my simulation. And the output, sorry, the input for my next sort of time advancement here. So we plug what comes out of this mutation process all the way back into my ODEs, and then advance time again by another capital T units. Repeat this, maybe have some extinctions, introduce mutation, advance it again by another capital T time units, and keep going. Okay, so that would be one mutation, two mutations, three mutations, and so on. So you had a question.
It was just about the case where we're not on a boundary in step 5.
Yes.
It says in the second sentence, I think, otherwise just choose a mutant to be one step above or below
Yes.
progenitor. I thought if we're not on a boundary, like we don't really have to do any further steps.
So if we're not on a boundary, we still have to choose which direction we're mutating in. So what I mean by if I'm on a boundary is, actually, I'll just go back up to that simulation here. So by this, I mean, if suppose my progenitor of my mutation is here or here, and I'm on a boundary of my system, then my mutant has to necessarily be this next step inside, right? Because I can't go outside my boundary.
Right.
However, if say my progenitor was over here, I now have to decide where is my mutant going. Is it going to be one above or one below?
Right.
So that's where I'm flipping this coin to see whether I'm moving one step up or one step down.
Okay.
Yeah?
Yep.
Okay. Very last slide in terms of lecture material. Okay, why might we do this? Despite what it might seem a little bit daunting to start with. I generally think it's harder to kind of take this sort of stuff in about like learning an algorithm just from like passively reading it on a slide or from me talking to you about it, which is why I want you guys to practice it over the next hour, okay? It's generally not as difficult as it might look once you actually get to the coding of things, okay? It is relatively straightforward to implement in the sense that, you know, hopefully you should be familiar with solving ODEs using an ODE solver. Now we're just doing that for many, many, many different phenotypes and most of them set to 0. Okay, so really what we're doing is we're just solving our ODEs for a little while, manipulating them a little bit with extinctions and mutations, solving ODEs. Manipulate a little bit of extinctions and mutations, solve your ODEs. Okay, so it's not super, super complex. If you can solve some ODEs, adding those additional steps of mutation and extinctions on are essentially just manipulating your initial conditions before you solve them again. Okay, so that in that sense is relatively straightforward to implement. If you can solve ODEs, you should be able to build up to this algorithm. Like the Gillespie algorithm, it's flexible to many different scenarios. As long as you can write down some ODEs, you can use this method, right? Because it's mostly deterministic, the only stochastic step we have is, you know, we progress time forward deterministically using our ODE solver by this capital T time units, and then you have one mutation, which is just one or two random numbers you need. And then you progress forward again by time, and then have one or two mutations. If you compare that to the Gillespie algorithm, to cover that sort of length of time, in the Gillespie algorithm, you're having to generate random numbers for all events, births and deaths and infections and so on, as well as mutations. Here, you're only generating random numbers for mutations, not for your births, not for your deaths, and all of those other biological processes. So it's much more efficient. This is not correct. That number 4 shouldn't be there. That's been copied over mistakenly from the Gillespie one. So let's just get rid of that. And this is as well. For some reason, the slide hasn't updated. The main advantages are up to here. This because it's mostly deterministic. It's very efficient. In terms of disadvantages, it doesn't really account for some of those individual level heterogeneities that we might care about in a simulation. That's why your Gillespie algorithm might be more valuable. It might not be very good if you have a lot of heterogeneity there, because then you've potentially got lots and lots and lots of ODEs to solve, which can slow things down. But those are the main disadvantages. Okay. Now is kind of practice time for you guys. This is just our interspecific competition model that we've met before. So I suggest having a go at coding this up, because we've done a lot of analysis about this. We know what our simulation should look like in terms of what do our singular strategies look like. We can vary these functions, perhaps choose the ones that we had in the last lecture for our competition function and our carrying capacity function. And use this to set up this adaptive dynamics simulation routine, okay? I'm going to be here, or rather we might move outside. I'll take a vote on that in a second. I will be here to answer your questions and help you get to that process, okay? So is everyone happy with that? Okay, cool. Can I have a show of hands? Who wants to stay in here? 1, 2, 3, 4. Who wants to go outside? 1, 2, 3, 4, 5. Who doesn't care? Okay, it seems like it's roughly even. So for the sake of people that want to stay in here, will stay in here. Yeah, okay. You're free to have a break now if you want, or you can get cracking straight away and start on it. Please just raise your hand if you want me to come around and give you some help, okay?